Hello everyone, I'm Koki Nitta from University of Electro-Communications. Today, I will talk about numerical verification method to construct local Lyapunov functions around non-hyperbolic equilibria for two-dimensional cases. This is joint work with Professor Nobito Yamamoto. In recent years, there has been a lot of research on combining numerical verification and dynamical system theory. These are reasons why such research have been studied. The following are examples of applications of numerical verification to dynamical systems. In this talk, we treat construction of Lyapunov functions for equilibria. Visual definition of Lyapunov functions. Consider the following system of ODEs, where f is the secant function and u is an open subset in Rn, and V star is an equilibrium of this system. If Shivan function L satisfies the following conditions, then it is called Lyapunov function. When the domain U is a bounded neighborhood of equilibrium V star, we say that L is a local Lyapunov function for V star. We want to treat saddle equilibria, so our Lyapunov function can take negative values. As previous work, there exists numerical verification method for constructing local Lyapunov function in quadratic form around hyperbolic equilibrium. These are features of the method. It can be adapted as long as the equilibrium is hyperbolic. It can be applied to both continuous and discrete dynamical systems. And it constructs a candidate for Lyapunov function by approximate computation and confirms that it satisfies the requirements of Lyapunov function by numerical verification. This is the definition of hyperbolic equilibrium. Our aim of this talk is to show how to construct local Lyapunov functions for non-hyperbolic equilibrium using numerical verification. Treating n-dimensional problem is difficult, so we treat two-dimensional problem. In this presentation, we also restrict the linear term to a specific form. We show concrete form in next page. As equilibrium is non-hyperbolic, its stability cannot be determined from the linear term. However, if a local Lyapunov function can be constructed, the stability near the equilibrium can be determined. In this talk, we consider following two-dimensional system of ODEs. This system, where V is a two-dimensional vector, J is this matrix, and Pk is a vector whose elements are polynomials of V1, V2 with terms of degree k. For this system, origin is equilibrium, and eigenvalues of the matrix J are plus minus I. I is imaginary unit. So origin is a non-hyperbolic equilibrium. We attempt to construct a local Lyapunov function for this system. The outline of our method is as follows. First, consider a nonlinear transformation by a polynomial and apply it to the original system. Next, for the dynamical system obtained by the transformation, construct a local Lyapunov function calligraphy L in quadratic form around the equilibrium of the transformed system. Finally, derive L from calligraphy L as a candidate for a local Lyapunov function around the equilibrium of the original system and verify a domain of L as a Lyapunov function through verified computation. For the system 2, consider the following transformation, where U is a two-dimensional vector and Qm is a vector whose elements are polynomials of U1, U2 with terms of degree m. From transformation 2 and original system 3, we obtain the following system of ODEs of U, where dm is a vector whose elements are polynomials of U1, U2 with terms of degree m. For the transformed system 4, we aim to construct the local Lyapunov function in quadratic form. Where Y is a 2x2 real symmetric matrix. Differentiating equation 5 with respect to time t, we obtain this equation. If the quadratic term on the right-hand side is negative definite, then calligraphy L is a local Lyapunov function around the origin. Let matrix Y be like this. The eigenvalues of yj plus j transpose y are them. So the matrix yj plus j transpose y cannot be negative definite. Therefore, we have to assign the values a equals 3, not non-zero, and b equals 0 in order to eliminate quadratic term. If the equilibrium is hyperbolic, we can determine the matrix Y so that J transpose Y plus Yj is negative definite. Next, we consider cubic term of time derivative of calligraphy L. This should vanish because it cannot take a definite sign. By considering the time derivative of U, we obtain this equation. P2 is a given term, and both JQ2 and DQ2JU can be controlled by the transformation. If we can find satisfying this equation for the given term P2, then it satisfies U transpose D2 equals 0. Assume that U transpose D2 equals 0. Then, if we can choose Q3 such that AU transpose D3 has a negative value for an arbitrary U non-zero. The function calligraphy L is a local Lyapunov function around 0. If we cannot select such a Q3, we aim to determine Q3 satisfying you transpose this equals 0. We determine Qm in a similar manner. When m is even, determine Qm such that you transpose Dm equals 0. On the other hand, when m is odd, check whether we can choose Qm such that you transpose Dm takes a negative value for an arbitrary u non-zero. If we can choose such a Qm, the function calligraphy L satisfies the conditions of local Lyapunov functions. If we cannot determine Qm such that U transpose Dm equals 0. Assume that we obtain a local Lyapunov functions calligraphy L by the above procedure. Note that there exists an inverse transformation from y to v by virtue of the inverse function theorem. A concrete form of the inverse transformation is described in numerical example. Let LV be a candidate for the local Lyapunov function around 0 in the original systems, which is derived by substituting 6 into 5 and omitting terms of degree higher than n plus 1. We verify the domain of LV as a local Lyapunov function by verified computation. We show the theorem to verify the domain of Lyapunov function. Consider homogeneous form of terms of degree to mhx together with interval coefficients alpha as like this. And define h upper bar by max of h. If h upper bar of y takes negative values for any y in this set, then h upper bar of x takes negative value for any x non-zero. We show how to use the theorem in numerical example. From now on, we show that we can choose appropriate Qm. The term Dm is calculated by like this, where p hat m is substantially given term determined from Pm and Qk. Let Pm be a vector space consisting of two-dimensional vectors such that each element is a polynomial of u1, u2 with terms of degree m. Define the mapping Nm like this. Mn is linear with respect to Q. We choose phi mi as base functions of Pm. Setting Qm is a linear combination of phi mi. We have this equation. Let calligraphy Pm be m plus two-dimensional vector space composed of all polynomials of u1, u2 with terms of degree m plus 1. And we transpose Nm of phi mi is a polynomial of u1, u2 with terms of degree m plus 1. It is elements of Pm calligraphy Pm. Let Qm be vector space defined as this equation. Qm is subset of calligraphy on Pm. If the dimension of Qm is equal to m plus 2, we can choose Qi satisfying this equation. Then U transpose dm equals 0. As for the dimension of Qm, the following theorem holds. From this theorem, there exists Qm such that U transpose dm equals 0 when m is even. On the other hand, when m is odd, the following theorem holds. From theorem 2 and 3, we can determine appropriate Qm. We show numerical example. We consider the following system of ODEs. The origin is a non-hyperbolic equilibrium of system 9, and the behavior of solution near the origin cannot be determined from the linear term. We attempt to construct the Lyapunov functions for the origin of system 9. This figure illustrates approximate solution of it. We cannot determine the behavior of solution from approximate calculate. We must choose like this, such that U transpose this equals 0. And we obtain P hat 3 and U transpose P hat 3. Therefore, it is enabled to construct the Lyapunov function. In order to A83 takes negative value, we determine A equals -1 and Q3 is like this. Using them, we obtain time derivative of calligraphy A is like this. The inverse transformation is as follows. Substituting inverse transformation 11 to Lyapunov function 5 and omitting terms of degree higher than 4, we obtain this equation. By considering the time derivative of equation 12, we obtain this equation. In order to apply theorem 1, we adopt the following inclusion. For V in this interval vector and interval dk and interval dk are this interval. Applying theorem 1 to the right hand side, we have proved that Lp is a local Lyapunov function within this domain. In conclusion, we prove that polynomials up to an arbitrary degree can be applied as nonlinear transformations for particular two-dimensional problems. One of our future works is to apply our method to 3 or higher dimensional problems. These are references of my talk. That's all. Thank you for your attention.